Okay, let's see. Where's paint? Paint. Okay, so this is the third amplifier, and maybe just everyone, since we've gone through a couple, if I give you just without breakout rooms, go ahead and see if you can go through. You want to circle each stage, decide what each stage is doing, and see if there's any tricks that each stage is doing, and anything else you know. So let's say till 2:25 or so, and feel free to ask questions, but go ahead and see if you can work through that and identify stages. This one's a little bit, there's, well, actually it's okay. This one's still, ignore the capacitor. Otherwise, take everything else into account. Okay, was that enough time?
I actually have a question. Below the differential pair, is
Mhm.
that a current mirror? Right, but yeah.
This right here, it's not a current mirror. Current mirror, uh, it consists of separate biasing circuitry,
Okay.
and then that generates a base voltage or a gate voltage, and that goes to a transistor. Right here, this is actually kind of embedded in the circuit, so it's not a traditional current mirror. It's a
What's it for?
it's a technique that actually increases gain, and you can only use it if you own if so right here it's a differential input, so it's two inputs, but it's a single-ended output. So only one of the outputs is being used. And if you're only using one output, this is a great way to increase gain and get rid of all the biasing circuitry that you would have needed for those NPNs.
Okay, that makes sense.
So, okay, so let's see. What was the first stage that you all saw?
Going from VCC all the way
Okay,
around,
okay,
and that's including that the current source, the differential pairs, and then that the thing you just went over
okay.
increases gain.
Yeah, nice. Okay, yeah, exactly. If you don't include any one of those transistors or current sources, it's not a complete diff pair. So diff pair is rail to rail. And this circle circle thing, what's that?
The current source.
Current source. And so in real life, in the actual circuit, that's probably a current mirror. Okay, and we're ignoring the capacitor. We'll get to that actually not quite today, um, but that we'll get to that either in today or Friday. What about next stage? What's the next stage? This isn't numbered, so it's hard to point out. But oh, anything special about this that you saw? The diff pair?
It's got Darlington input
Yeah.
transistors,
And why do you like Darlington pair input transistors?
more gain and more RN.
Yeah, mostly the high RN. Darlington pairs can provide the current if somebody asks for it, but in this case, what's actually controlling the current is this.
Oh, that actually makes sense. Yeah.
It's kind of limiting, even if these say, hey, I can conduct 5 amps. If this was only conducting a milliamp, there's no place that these can get that 5 amps. So it's actually limited by this current and then split between the two sides. So yeah, if somebody asked for a bunch of current off of here and it wasn't limited by this, these things would give you tons of current. So exactly. All right, and then the next stage.
Wait, so the reason that those Darlington pairs are there is to increase RN, right?
Yes. Okay. What about the next stage?
I'd say the buffer. I'd say it's a buffer stage, including the two common collectors and the current source. I'm not sure if the
Okay.
common collector is in the same stage, but I know it's to help shift back up. Like it's a level shifter.
Could
So,
be a level shifter here, but just to circle it, it's
yeah.
just one stage at a time.
Okay.
And
It could be for impedance matching too, correct?
not impedance matching, but impedance transformation. So it's got so many different names. In this case, if there's just a common collector in the middle of your circuit, it's probably because they tried to connect two stages and the second stage was loading the first. So, oh, we've got to fix that. Let's just throw in a common collector. I'm not sure if that answered the question. So this is a diff pair, and this is for a big Rn. And it gives you some gain, so that's nice too. And then this stage again is a kind of amplifier is that?
Common collector.
Common collector. So this is a common collector. And in our case, since the first common collector we saw didn't have a current source here, this is a little bit different than the current common collector we saw with the resistor. And let's draw it out here again. I'll flip it to an NPN so it's easier to see. This was our original common collector. And this one, because there's a current source under the emitter, actually, should move that over. Ha, not sure what just happened here. Right, so let's move this over to step by step. In this particular version, there's a current source underneath the emitter. And this is some V bias. So what's the Rn of this common collector, the one on the left here?
Would it be R pi?
Okay. But in this case, there's a
Plus-
resistor below the emitter. Yes, exactly.
Plus Re times 1 plus beta.
Yes,
Times beta.
exactly. So that's for the one on the left. What about the one on the right? What's its Rn?
It's kind of the same thing, but then instead of Re, it would be the perceived resistance at the
Okay.
emitter
At the collector.
or collector. Sorry.
Yeah, and what is that? Remember his quick method, the resistance at the collector?
Is it Ro?
RO. So this one would be, since this transistor looks down and sees a resistance of RO, it's in the same place RE was, and you get a much bigger Rn. So this current source right here, it's this thing. So what's a good color? Blue. So this thing right here is this thing right here. Okay, so the current source makes this a much bigger Rn, and then it's much less likely to load your diff pair. Okay, good up to there? Questions? Okay, what's the next stage? This one's tricky. This one's a little bit tricky.
Is it a common emitter?
It's a common emitter. What's special about it?
It's got a wonky Darlington pair.
Yes, the wonky Darlington pair is so much better than I could have named it. Yeah, so this is a common emitter with this bottom transistor replaced with a wonky Darlington pair. And usually you would see this connected over like that. But as long as this thing can get current from someplace, it still provides that current to the base and turns up the current through this other transistor. So that looks good. Okay, so this is a common emitter. And what kind of load?
Active load with the current mirror.
Active load with the current mirror. So wherever you see a current mirror, that's the same as an active load. Okay. So I've got our input stage, common collector, which is, I guess, just an intermediate stage. Then common emitter, what stage is that? What kind of stage?
Gain.
Gain. So we got our gain stage, which leaves, what's our last stage?
The output stage.
Output stage. Okay. And what did you see for your output stage?
Like I guess an ugly push pull.
An ugly, possibly ugly.
Sorry, I don't know if that's offensive or not.
I don't think it's insulted. Okay, so this is an output stage and it's a push pull. What's the voltage you need? So to get rid of crossover distortion, what's the voltage you need to get from, let's make it red. How about red? So when you're looking at whether there's crossover distortion, you look from, you have, for the push pull, you have two inputs and they have to be separated by a certain amount of voltage. To figure out that voltage, you find your push pull and you travel inside of it from base to base and figure out what the voltage difference is there. So what's the voltage difference base to base if that resistor is pretty small?
Like 3 VB on.
3 VB on. And so question is there crossover distortion?
Yes.
Yes. And why is that?
There aren't enough transistors, or I guess you could use diodes instead. So there aren't enough VB ons being supplied from that base to the bottom base.
Yes. So if you're trying to see if there's crossover distortions, so to figure out how much voltage you need, you go inside the circle. But to see if you have crossover distortion, then you find a path from one base to the other, and there has to be 3 VB on difference between those two. But is there? Nah. There's no. They're tied to the same voltage. So this will have crossover distortion. Okay, and then last part here, what color did I not use? Green, I'm all out of colors. Gray, pink, does pink show up okay? Right, then there's this thing again. What's that thing? I'm making a mess out of this, aren't I? What's that thing?
Is it for diverting current?
Yes, and I still don't have a good explanation for that. It's still on my list, so I apologize. I'll still planning on coming back with a good explanation for that. But yes, instead of current going down into this base or into this base, a bunch of it gets pulled off. And so there's less current for the bases, but I'll try to find the math for that and give you a better explanation. So was that easier than the first two? Starting to get comfortable with it? Maybe? Okay, I got a thumbs up, yay. Okay. All right, so I'll make sure to post that. So that's the first thing to do today. Just, I think, just looking more and more amplifiers will not only help you when you're having to pick an amplifier in the future, it'll also help you if you ever end up designing one for work.
Professor, I have a question about that last stage and
Okay.
just in general, what push pull are you for? The only thing I remember from lab learning is that they just have higher power efficiency and that you need to, try and avoid like any distortion. But I don't know why that's particularly used over any other amplifier.
Okay. Yeah, the main thing is the power. Let's do a quick one because I actually didn't do it in class. So let's do a we'll do the simplest version here. And this should be RLs representing whatever the push-pull is connected to. So you'd have your circuit, and the last stage in your circuit would be the push-pull, and then you have another circuit over here. When you connect it to this other circuit looks like some resistance. So this resistor, this RL right here, is showing the resistance that this circuit would see if it was connected to another circuit. So it's actually not part of the circuit. It's just imitating a fake circuit on its output. Okay. So you have that, and let's just do, and again, diodes are usually implemented as diode connected transistors. Let's just do something like this. Okay, so what happens is, oh, sorry, this is bad. If this is VCC, you always want this to be in the middle. So you don't want this to be ground right here. So what happens is if V in, so let's do cases, see if the pens come back. Oh, yay. Okay, case one. V in greater than VCC over 2. So if V, you can think of the default voltage here. If you don't know what the voltage is here and you're looking at a push-pull, just assume it's whatever this voltage is. It may be a little bit different, but it's going to be somewhere around there for starters. It's the safe voltage to use as your approximation for that node if you don't know what voltage is actually on there. So if V in is greater than VCC over 2, then for this bottom PNP to turn on, the emitter voltage of the PNP needs to be higher than the base voltage of the PNP by a VB on. But if this is VCC over 2, and this is VCC over 2, and this, sorry, I should make this clear. This is a VBE on drop, and this is also a VBE on drop. So if this is a little bit over VCC over 2, and you subtract a VBE on, there won't be a VBE on across your PNP. Did I go too fast?
No, that makes sense.
Okay, so the PNP's off, but if you're above VCC over 2, and then you shift up by a VB on, the NPN is going to be on. So in that case, what you have is the NPN on and the PNP off, and what you get is you get this circuit. If we're calling this V out. So if the PNP is in cutoff, it's like it's not there, and you actually get this circuit. Okay, and what is that circuit?
Common collector.
It's a common collector. And what's the voltage? What's the highest voltage and lowest voltage? What's the highest voltage in this circuit? It's VCC, and then the lowest voltage is this VCC over 2. So the voltage across your circuit is actually VCC over 2. Okay. Then let's look at case 2. Case 2, and that's when V in is less than VCC over 2. And what happens if V in is less than VCC over 2? What region of operation is the NPN in?
Is it off?
It's off. Okay. And then the PNP is on, so the circuit you get there looks like this. And what's that circuit?
Common emitter
Is it a
or
common emitter?
common collector.
It's a common collector again. So a push-pull is actually just it's either one common collector's on or the other common collector's on. And you get the same thing here. Your highest voltage is VCC over 2 and your lowest voltage is 0. So the voltage across your circuit is actually VCC over 2. Okay. So where the power saving comes in is because these are both common collectors, your R out's going to be the same as if you just used a common collector. Do you agree with that?
Yeah.
Okay, so when the push-pull's in normal operation, it's either the top common collector's on or the bottom common collector's on. But let's see what happens with just a regular common collector. So you're still going to get your 1 over GM for your R out for the push-pull. This one, your R out still going to be 1 over GM because you see an emitter there. But what's your delta V sup now? What's the highest voltage in your circuit?
VCC
And what's the lowest voltage in your circuit?
0.
0. So what happens is if you use a single common collector, you have a voltage across it of VCC. But if you use the push-pull, you only have a voltage drop across it of VCC over 2. And if you remember, power equals IV, and the voltage across the common collectors for the push-pull is half of what it is for a regular common collector. So you actually use half the power when you use a push-pull.
Okay. Thank you.
Okay.
You have the same amount of gain, or you're not losing gain at all in any way, but
No.
you are saving power. Just you're using less voltage. That's the main thing.
Yes.
Okay.
You can still argue that because of the 2 diode drop you have to get, you have another branch that's conducting. There's arguments that it actually uses as much power or more than a common collector if you include the biasing circuitry, the 2 diode drop branch.
Uh-huh.
But yeah, lots of times, yeah. Anyways,
Thank you.
So you can argue both ways.
Thank you.
Did I turn the recording back on, by the way? Nope, I did. Okay, good. All right, so that's push-pull. Does anybody else have any questions on push-pull? It's actually just 2 common collectors, just only one's on at a time. Either the top one's on or the bottom one's on.
I have a question.
Okay.
So on the circuit we were just talking about, if you pull that up, there's a Darlington pair. And so I think you said there's like 3 VBE on. And so in order for it to work, you need a 3 VBE on difference between the VNs, right?
Yes.
And so you basically have to trace it from the VN of one to the VN of another, right?
Yes.
Like that red line you drew right there,
Yes.
like traced through the output stage.
Mm-hmm.
And then you need that same difference between them?
Yes.
Okay.
And the idea is that your VN, if it goes a little bit above, right here I had VCC on the example below, I had VCC over 2 on the output. If the input goes a little bit above it, you want to turn on the top common collector. If you go a little bit below, you want to turn on the bottom common collector. So you want them to be where they switch on and off.
Yeah.
You want a common point.
Well, only one is on at a time.
Yeah. So that's why you need that offset. That was a lousy explanation, but did that make some sense?
Yeah.
Okay. Any other questions on common collectors, push-pulls? Okay. 10 minutes. I always do this, right? Right. So the next thing to talk about is this other handout that I have online. It's the one called frequency response. And it's actually not frequency response. I should have named it capacitance. Okay. So that's the document I'm looking at right now. And let's see. Do I have a picture? I don't have a picture. Let's draw a picture. So for a BJT, I'm going to try to talk fast and see if I can get through all the capacitance. Okay, so in a BJT, it has 3 PN junctions, and this is pen stop working again. So we got a P type. If this is an NPN, it's a PNPN. And for all BJTs and all regions of operation, this PN junction right here is it on or off between the collector and the substrate?
Always off.
Always off. So what happens is you get, if I can do something fancy here. Whoops, that looks big. Whoops, I don't know. You get a depletion region around here. That didn't work very well, but you get a depletion region. And what happens is this N-type region, that's behaving like a conductor. The P-type region is acting like a conductor, but this depletion region, it's devoid of charge and it's acting like an insulator. So you have a conductor, this might be your collector, and then you have the substrate, and then you have an insulator between them. What's that look like?
A capacitor.
A capacitor. So but that depletion region, you need that, need those PN junctions to create these transistors that work so fabulously in other ways. But whenever there's a junction that's off, you basically have a parallel plate capacitor. And we're always dealing in the forward active region, so this would also have a depletion region here. Both the CS junction's off, and the BC junction is off. So those are just parallel plate capacitors. And then this junction right here, it's actually in the forward active region. This is conducting. So you say, oh, so there's no capacitance. But unfortunately, when you change the voltage across that junction, it takes some time for electrons to move around. And that behavior of having to wait for the electrons to move looks capacitive. So just like when we had a transistor that we're saying, hey, this looks like a big resistor. It's not actually a resistor as we know it, like a traditional resistor, but it behaves like a resistor. Same thing here. This is not actually like a parallel plate capacitor, but because it takes time to adjust to a new voltage, it's acting like capacitance. So you actually have 3 capacitances here. You have CBE, CBC, and CCS. And in 306, your BE was C pi, probably called it C pi. That's a more traditional textbook name for it. And CBC was C mu, and CCS is just CCS. Is it okay where capacitance is? So let's look at how you would calculate that. Turns out your model file, yet again, gives you important values. There are equations. I don't think you saw them in 306. Maybe you did, but even if you ask me where they came from, I just say, go ask Braun. So right here, I'll just say, hey, these are the equations. For the, remember there is base emitter capacitance. And remember, that's actually an on junction. So it's not a parallel plate capacitance. And this is the equation for the base emitter capacitance. And it has two constituents, if that's the word I want. And the first constituent is this equation right here. It's 2 times the area of the emitter times this CJE0. You say, well, what's CJE0? Well, guess what? Model file gives you that value. Okay. The emitter area is actually something you have to be given. So it's not in the model file. So if you get a problem and they're asking for the capacitance, you have to say, well, I don't know what the area is, so I can't calculate the capacitance. So somebody has to give you this area of the emitter. And then the second part of the base emitter capacitance equation, that's this, I wrote it down, I always forget it, the base transit time constant. And guess what? Model file. That gives you your value for that. And then it's times GM. So that's just your IC over VT. Just like you've been, the GM that you've been using so far. You add those together and you get the capacitance for base emitter. You also have for the, you had 2 more capacitances. You had the capacitance along this junction. And that equation is AC. Again, anything with the area here, somebody has to give that to you. That's not something that's in the model file or that's a constant or anything. It's whoever drew this transistor, they made it a certain size. You have to get that size from the person that drew it. So this is the area of the collector times the zero biased BC junction. And that one I think it's CJC. Now I'm doubting myself, but CJC, I think. And then you have some VCB over this side, and I wasn't able on a quick search to figure out what value this comes from in the model file. So I would probably give that to you, but it kind of a traditional value for these 2 values right here are 0.75 and 0.9, for example. And then from there, it's an easy step. Just plug it into the equation and you've got the capacitance. And so I put an example here. So this is, again, if somebody doesn't give you the areas, you can't do the calculations of the capacitance. And right here, this gray square right here, that's the emitter. So if you look at that, the emitter is 0.6 by 2.4, and those are micrometers. They should be. I don't see units on this picture. Micrometers, okay, yeah. So that's the area of the emitter. So if you go back up, remember we had that equation that used the area of the emitter. As long as you have the model file, now you can calculate that capacitance. And again, probably femtofarads or picofarads. Okay. Yeah, so I've got this example here. And then for the actually on the handout online, I realized that I didn't finish this equation. So I'm sorry about that. I'll fix that and update it. But if you're looking at the handout, this number right here isn't on the handout. It's a typo, I left it out. But yeah, here's just some examples of calculating from a model file, calculating the base emitter capacitance, the base collector capacitance, and the collector substrate capacitance. So that was kind of a dash through BJTs. next time we'll start with the MOSFETs. We'll do MOSFETs next. But any questions on capacitance on the BJTs? We'll see how to use that too, to figure out capacitance is the new thing that's going to be added to see how fast our circuits can run. Okay. Good. Okay. Thumbs up. Okay. Then I'll stop here. If there's any questions, feel free to ask away.
Thanks, Professor.
All right. I'll see you later.
Thank you, Tina.
All right. Bye-bye. It's kind of fun watching everybody disappear.
Professor, actually, I had a quick question.
Okay.
This doesn't really relate to like circuitry, but just in general for the class, for the homeworks that we turn in that is with a partner. I've been like turning it like either I turn it in or my partner turn it in. Is that how you wanted it, or did you want both of us to turn it at the same time?
As long as both of your names are on one, you should both get credit. Are you both getting credit?
Personally, I'm not. For some of the assignments that he's been turning in, I don't know if it's for some of them or all of them. I'd need to like check which ones he turned in and I turned in for the past quarter. But there's definitely like a few they're missing, even though both our names have been on every single assignment.
Okay, can you send me just an email with your name and your partner's name, and I'll pass that on to the graders. They've been really good about going back and filling in the blanks.
Perfect. I just want to make sure like everything's in order, like before like they sort of talk about like finals happen. And also, do you have any so we're gonna have this midterm, and then we're gonna go into your Zoom, and like we're gonna talk to you about like the problem of your choosing. What about a final? Like, are we gonna have anything similar for like final exam, or what's the idea behind like end of quarter assignment?
So the frequency response is really the next big topic, and I'll just give you a big homework on that. So you have practice and you have something to ask questions about.
Okay, sweet, perfect. Okay, and then I'll send you that email right now then. Sweet, thank you so much.
All right, no, thank you. Sorry about that.
Oh, no worries.
Okay. Right. Okay, messed that up. Now we're recording.
I have a question.
Okay.
So when we have, I guess I'm just kind of confused about crossover distortion. Is crossover distortion usually part of the output stage, or are they usually considered separate things? Does it make sense?
You can consider it kind of the diode connected transistors, the diodes. You consider that kind of the biasing for the output stage.
Okay.
I guess in its purest form, just two transistors is your push-pull.
Okay.
But then you're setting the inputs, that's biasing. I'm not sure what the official definition is, but considering every textbook I look at gives a different definition for 20 different things than I learned. Just as long as you can recognize it and know how to make it succeed and run correctly, then I think but I think in the purest form, it's just those two transistors.
Okay.
And the diode connections are the biasing, consider biasing. Okay, so I guess that's the answer, that it's a push-pull.
Yeah.
Okay. Now, the tricky part is which transistors make up the push-pull.
Yeah, that's where I get really confused. That's why I was asking that question.
Okay. What do you think? Should I just give it a go? We'll see. If my pen writes, then I'll answer it. If my pen doesn't write, then you have to answer it.
So for the crossover distortion, anyways, I'm pretty sure it's those top two, the Darlington pair, and then the bottom one.
Exactly. You got it. So, well, there we go. So I agree. That's the push-pull right there. And then to figure out, how do you figure out what voltage you have to have between, oops, what's going on? Between here and here. So the important thing to get rid of crossover distortion is to find the two inputs and make sure they're a certain voltage apart. But how do you figure out what that voltage is?
You follow from the top one to the bottom, the top base to the bottom base, and count your VBEs.
Okay, exactly. And how many VBEs is that?
3.
3. And are there 3 VBEs between the two bases?
No, but they might just not be showing us, like you said last time.
Okay. Yeah, these are actually the same wire. These are shorted together, so there's clearly not 3 VB on. So as how they have it drawn, yeah, there's going to be crossover distortion. Let's try. Oh, my dog just farted. I'm really sorry. This is one time you're glad you're in another room. Oh my goodness. Oh. Okay. What's that doing? The yellow circled stuff. What do you think that's doing in the
It's
circuit?
protecting.
Exactly. And then again, how does it turn on? When does it turn on? When does the protection kick in?
Voltage across the when the current increases and the voltage across the resistor increases to VBE on, that other transistor turns on and diverts the current.
Perfect. Yep. Okay, so getting that went pretty quick. Starting to get a feel of how to divide it up into stages and things like that pretty comfortably? Okay.
I have another question.
Okay.
So when you say crossover distortion, is that the same thing as saying push-pull? Or
no, the push-pull has to do with this output stage being 2 common collectors stuck together. So either this one's working or this one's working.
so the push-pull has crossover distortion?
If it's not biased well.
Okay. Okay.
So if there were the three VB on drop here, like 3 diodes here, then it would still be a push-pull, but it wouldn't have crossover distortion. Right now it's a push-pull with crossover distortion. But if we put the diodes in right here, then it would be a push-pull without crossover distortion.
Okay, that makes a lot more sense. Thank you.
All right, good. Any questions? The rest of you are quiet today. All good? What's the cap for? Okay, so the cap is going to, thank you. The cap is, we're gonna start on capacitance today, and on Friday, it will make more sense to you. I'll post the lab, pre-lab talk. I actually talked for like an hour in lab yesterday. I apologize yet again. But it went through kind of a quick version of what we're going to be talking about in class. So I can post that too. But we'll be talking about that on Friday. It has to do when you hook something up with feedback. Sometimes you get a problem where your circuit's unstable. Have you had 302? Okay. If you've had 302, then you've seen where things can oscillate when you hook something up with feedback. That capacitor is to keep it from oscillating. We'll see how to, oh, I see, that was privately to me. That's why it's probably mysterious to everybody else. Yeah, somebody asked what the cap was for. Okay. But yeah, it's to make it stable once you hook it up with feedback. If you're not using feedback, you don't need that capacitor. And one thing that is, I don't know if it's interesting. I looking for a word to come after that, but an op-amp can also be used as a comparator. If you go to DigiKey or Mauser and buy a comparator, the difference is that it doesn't care about a low R out, because so a comparator is considered a circuit all on its own. A comparator isn't made to be hooked up with feedback, so it doesn't care if its R out is low. So the difference between a comparator and an op-amp is that it probably doesn't have an output stage. It probably just goes gain stage to the output. And also, it won't have this capacitor in it. So a comparator and an op-amp are basically the same thing, but the comparator doesn't have an output stage and doesn't have the capacitor in there, probably. More information than than you asked for, probably, but yeah. I always wondered that, and then one day somebody helped me out, cleared that up for me. Okay, so if there's no questions, any more questions on this? Okay, then on to not Polylearn, on Canvas, there's a document called frequency response. And I'll be working off of that for next few minutes. I think we are 15 minutes ahead of the other class. So I forget what I babbled about at the beginning of the last class. Oh, there was like 2 minutes we talked about, like, if suddenly we found a vaccine that we can mass produce and everybody gets vaccinated and we come back in fall, what will be strange? I think I'm going to have some PTSD after this, actually.
It's going to be hard hearing people talk around you all the time, I think. Like just constant conversation, noise, people. You don't hear that very much at the moment.
In the library? Yeah, I don't know. I'm gonna PTSD it, I'm pretty sure, for a little bit. Then I'll forget. I forget quick. There was a study that did they whacked a caterpillar, and the caterpillar would recognize for like 3 seconds that the finger meant something bad, and then forget. Like 3 seconds later, you could whack it again, and it wouldn't remember that it had been whacked. But dogs remembered like for 7 minutes, and cats for like 13 minutes. So I think I'm a caterpillar. I think once we get back, I'll forget pretty quick. Okay, so frequency response. The handout is what I'm going to be going off of now. But let me talk just a little bit on this. So for next topic that we're going to be looking at is frequency response. And so far we've been using really low frequencies, so we haven't really been worried about what the capacitance in your circuit does to the signal, but that's the next topic. And it turns out that almost any circuit, can I say any circuit? Okay, a guarded every circuit that you use is actually a low pass filter. So when you're changing the voltage at a node, you're charging or discharging a capacitance, and that current comes from someplace, and it's limited by a transistor or a resistor or something. So it looks like an R onto that C. So if you're charging up a node, if you're making a voltage go up, you're charging that through a resistance. If the voltage on a node is going down, then it's actually discharging through a resistance. And either one of those looks like a low pass filter. Okay, so we've got to figure out to figure out the frequency that our circuit can run. We need to figure out how to find the perceived R and the perceived capacitance at a node. So to do that, first of all, we have to look at the sources of capacitance, and transistors give you a lot of capacitance. Wires give you capacitance. Everything gives you capacitance, basically. But let's look at BJT first. So BJT has the emitter, has a base, has a collector, and then it has a substrate. Okay, and this class, we're doing forward active. All of our transistors, we want them in forward active. They give us the best current sources. They give us the best gain. That's where we want them to operate. So let's look at that. If we are in forward active, or actually any region of operation, actually, let me draw this in. So the substrate, if we're looking at NPN, the substrate would be P. This is N, this is P, this is N. In any region of operation, is this PN junction conducting or not conducting?
Not conducting.
Not conducting. So, and when it's not conducting, what forms around the? This is kind of cool. I like this spray paint. What forms on the PN junction?
Electrons or electron holes potentially.
In
Oh,
between the PN junction. Should we do the sound game? D. Yes. Who said that? Somebody said that. Okay. So that, the depletion region. So what happens is this is a conductor. You dope it N-type, it's got extra electrons, so it can conduct. The P-type, it has extra holes or a lack of electrons, so it can conduct. And then in between, there's this region that's devoid of charge, so it acts like an insulator. So what you have is your collector, that's a conductor, and then you have an insulator, and then you have another conductor, whoops, which is your substrate. So what's a conductor, insulator, conductor?
capacitor.
So this whole thing right here is a capacitor. And then if you're in the forward active region, do you remember what happens to this junction? Do you remember whether it's conducting or not conducting? This is something that I got asked on one of my exams in school. So I will remember it till the day I die. Right.
Sorry, what was the question?
If this is in the forward active region, this transistor, is this PN junction between the base and the collector, is that conducting or not conducting?
Conducting. Not conducting.
Yes, exactly. So oops, oh, now it's, okay. Apparently this depletion region is a different color. Yeah, so that one's off. So that one too, it just looks like a parallel plate capacitor, whether you want it to or not. If you're operating a transistor in the normal region of operation, you have two capacitors here. What about this? In the forward active region, is this junction conducting or not conducting?
Oh yeah, that's conducting, all right.
That's conducting, yes. So so you'd say, okay, so that one's conducting, no depletion region, so there's no capacitance. But there's capacitive behavior. Just like when we were looking at a transistor, we said, oh, when we change the voltage, the current changes this much. That's resistive behavior. It's not a resistor. It's not like a traditional resistor, but it has resistive behavior. And actually, the same thing happens here. When you change the voltage across that PN junction, it actually takes some time for electrons to move around, and it behaves like there's a capacitor there. So there's not a parallel plate capacitor like you know, but it has capacitive behavior. So even though not really capacitor here. It's considered capacitance, capacitive behavior. So if you want to calculate that, that's where this other handout comes into play. And these equations right here, I'm going to introduce in it, depending on which, you know how you have model files that you use in LT-SPICE and all that? Depending on which models those use, these equations are actually different. And I grabbed these equations from an old document, but I looked up some of the newer equations and they're not the same. So depending on which version of the simulator you're using, these equations might or might not be valid. But this is an example of the equations. Okay, so the base emitter capacitance, so again, coming back here, the base emitter capacitance, so that's this one, use purple, that's this one, the base emitter capacitance. To calculate that, you've got an equation that adds up two things, and each one of those things has its own equation. And the equation of this first term is 2 times the area of the emitter times CJ0. And you say, okay, well, wait a minute, where are these values? Area of the emitter, somebody has to give that to you. It's not in the model file. Whoever designed that transistor knows the area and has to give that to you for you to use this equation. But this other value, that is in the model file yet again. And that's this value right here. And for, if this value isn't given to you, here's a reminder. If this value isn't given to you and you try to simulate a BJT in LT-SPICE, what happens?
It's just going to assume some like preset.
Exactly. Yeah, LT-SPICE has default values for all of these things. If you don't specify it, LT-SPICE uses their default value, and I think the default value is actually 0 for this. If you want to know, put a link to it someplace. Let's see. If you go to LT-SPICE users manual, I have a few windows open. This first one from Colorado, ECEE Colorado, this is the one to look at, the SCAD3. And if you go into that document, I think it has to do with the 1,000 tabs I have open, but my computer has slowed down again. So if it crashes, I'll come back. But maybe I should just let oh, there we go. Just had to threaten to leave. So to figure out what those values are, if you go to this document and you go down to this chapter on circuit elements, this A, B, C, D, E, F, G, H, I, J, K, those are all, remember voltage sources? Their name always has to start with a V. BJTs, their name always has to start with a Q. MOSFETs always have to have a name starts with an M, inductors L, resistors R. When you name something, it has to start with one of these letters. But the other thing is that you can go to page 145. That's the BJT section. And it gives you the syntax. But if you keep going down, then you get to this table. And if you don't specify, it's default. If you don't specify a beta, it uses 100 for beta. If you don't specify a saturation current, then it uses 1 microamp. And for the capacitances, let's see, what's it use? Yeah, so it uses 0. If you don't specify a CJE, then you have 0 capacitance and your BJT runs infinitely fast. Okay. So I'm going to close this just because it got slower when I opened that. But that document, I think I have a link to it on Canvas, but it's very helpful. Okay, so you have this value. Somebody has to give you the emitter area. So area subscript E means the emitter area. And then the other term, the second term right here, that has to do with the moving electrons. And that TB is the base transit time constant. So you take that constant and multiply it by GM, and that gives you the value of the second term. And you just add them together, and you've got the capacitance on the base emitter junction. Is that okay?
Is the transit time? I know that. I mean, I guess the CD is already in there. Oh, okay. Transit forward. Okay. Thank you.
Yep. Okay. And then there's also equations for the collector base and the collector substrate. And I couldn't figure out where the size coming from. But traditionally, this value down here is like 0.75, sorry, for the collector base, it's 0.75, and like a typical value for the collector substrate is like 0.9. So until I figure out where the size come from, we'll just go with, assuming that it's somewhere around these values. But these equations, again, you've got the area of the collector and area of the, what's T stand for? Transistor, I guess, the entire transistor. Those have to be given to you. Okay, and then I put in an example, and here's a BJT, and this gray square right here, I don't know, can you see where I'm pointing to? That is the emitter. So remember that first equation had the A subscript E, the emitter area? That would be 0.6 times 2.4 micrometers. That's the value you would use. So if you had this diagram and you wanted to find the capacitance and you had the model file, you could do it. Okay. One last thing on the BJTs. On the handout that I have on Canvas, I forgot to put in this value. I just wanted to research that a little more, so I didn't finish it in the handout, and I still don't have an answer. But I'll update the handout and post it with this value put into the handout. But I apologize for that. Forgot to finish that up. Okay, and these are examples of the calculations you might go through to find the capacitance. And it's going to be for a single transistor, femtofarads, picofarads, somewhere around there. So for BJTs, finding the collector base capacitance or the base emitter or the collector substrate capacitance. Any questions there? Okay, so let's, all right, the MOSFET capacitance is, what should I do? What should I do? Actually, let's just do an example here, how you would use this. So we've got these three capacitances. You've got the base emitter. You've got the BC, CB, doesn't matter. And you've got the CCS. And in 306, you may have seen capacitances. The BE was probably called CPi. Most textbooks use CPi instead of CBE. I'm not picky, but if you go to an interview or something, you probably want to know textbook name. And then CBC is often called C mu. Okay. So let's see. There's two directions I could go here. Since we have 3 minutes left, we're ahead of the other class. So let's do. I'm gonna do this. I'm gonna do this. That's a little bit smaller. So you see it all, right? So how this would be used. That's supposed to be ground there. So we know we have these three capacitances. Now, if I asked you the capacitance of V in, and this is kind of a lie. I'll correct this on Friday. I'm ignoring what's called the Miller effect. But if I want to know the capacitance on V in, what you do is you come back to this picture, and I know there's a capacitance called CBC or C mu here. I also know from the base to the emitter, we have C pi. So if I wanted to know the capacitance on the input, I would say, okay, the input's connected to the base. Okay. Then I'd go and I'd put myself on the base here, and I'd say, hey, what capacitances are directly connected to the base? And I see two. I see C pi, and this is, oh, that will stay. And then I see C mu. And this one's going to actually change due to the Miller effect, but for right now, those are the two capacitances I would see. So what about if I wanted CV out?
Would you not see them in parallel?
Yes, so they'll add. So capacitors in parallel will add. All of these capacitances, you can kind of take them as being connected to ground. This is a lie right here, so lie. That's the only one that's special because it's connected to the output and the output's moving too. But what about CV out? How much capacitance is on the resistor?
None.
Yeah, we'll say none. In real life there is, but we'll ignore it for this. Okay. And then what were you going to say?
So sorry, I think so. Like you would see them in series, but those two capacitances in series, right?
For this one, this is connected to the base, and this is connected to the base. We'll figure out a multiplier to put in front of here, so you can consider this connected to the base. And if you have two, we'll figure out a multiplier here that makes this like this was connected to ground. I meant to say ground, not base. So it ends up that you have two capacitors here connected to ground, and when they're in parallel, then you just add them. But we'll need a multiplier here to make that true.
But for CV out,
Okay.
would they not be in series for CV out?
No, you will only need to look at the capacitors that are directly connected to whatever terminal you're on.
Okay.
Oh, we're over time. I forgot. Okay, so what capacitances are directly connected to the collector?
CCS and C mu.
Yep, and you're done. And C mu is a slight lie, but this is generally this is pretty good. But this one you're going to need a multiplier out here. So that's how you would figure out the capacitance on a node. Okay. So next time we'll start with the MOSFET, and then we'll see how that gives you your frequency response of your circuit. So good questions? Okay.
Thank you. Have a good day.
All right. Talk to you later.